this problem is a little bit tricky. The first thing we want to remember is that we're looking at a confidence interval. We're looking at the margin of error, and we want to figure out what the z-score, the critical value that is going to be for this particular problem. So we can remember that our margin of error equals our critical value, in this case is z star, times the standard error, which is p hat times 1 minus p hat, and that's going to be all over n. So we have the numbers that we need. The margin of error is 0.04. We do not know the critical value. That's actually what we're solving for. Essentially, that's what we're solving for. And now if we plug in our p hat, we get 0.28. 1 minus that is 0.72 divided by the sample size, which is 450. So this is all well and good. And now what we want to do is if we go through and solve, we're eventually going to find our z star is 1.8898. And again, that doesn't tell us exactly what our confidence level is, but we can do one of two things here. One of them is going to be a little bit more challenging. The other one is kind of, if we use our intuition, it's very fast. So if I look over here on my Z table or table B on in your reference, you can look to see where 1.8898 is going to land, and you only look at the bottom row, and it lands somewhere between the 90% confidence level and the 95% confidence level. So this is going to be, let me see, my confidence level, I'll just put CL is going to be, there we go, somewhere in this range. Now, numerically, it's going to be a lot closer to 95 than it is to 90%. It's not as high as 95%, so I can cross these two out. It's not down at 70%. It's closer to 95 than to 90, so my best answer here is 94.1. If you want to get this absolutely correct, you have to be careful, because one thing that can go wrong, if you do, at this point we could do a normal CDF calculation to figure out what the precise confidence level is going to be. Because what we're saying is essentially we have this normal distribution centered around our p hat, and I've got this 1.88, which is sitting right around here. So here's my critical value. But if you just take the area of everything below this, yeah, the answer is C. If you just take the area of everything below this, that's actually not correct. You're actually going to get closer to 97%. So you might be tempted to think that there's a 97% confidence level. But keep in mind, what your critical value is telling you is how many standard deviations away from the mean are we going. So the whole point of me saying that is that there's going to be another area down at the low end that you need to get the area of, sorry, that you need to exclude. So what you want to do is, if you're going to do a normal CDF to figure out what the exact confidence level is going to be, you want to make your confidence level go from a lower bound of negative 1.8898 up to an upper bound of positive 1.8898, because remember, this is the number standard errors away from the mean, not just a z-score that's measuring up from negative infinity. So if you do a normal CDF real quick, and I haven't done this part yet, so let's hope I'm not lying to you. If I go from negative 1.8898 up to 1.8898, I should get 94.1, and we do. So that represents a 94.1% confidence level. But again, this is a little bit of extra work to get it 100% exact. If you can just kind of use your statistical intuition to say it's between 90 and 95 and it's closer to 95, therefore the answer is 94.1, well, that can save you some time and you're probably going to feel pretty confident with your answer. Okay, are there questions on this? Because this is a little bit of a strange question. Okay, then. Clear this and we'll move forward. So to start this off, we are going to be re-expressing data. And this is all from chapter 10. I don't know if you guys are paying a lot of attention in your textbook. Speaking of, did you bring my textbook back?
Oh, right here.
Get it out right now.
I was going to use it.
No, I don't trust you. Okay.
So honestly, I didn't really expect it to go as mine or yours, but I just grabbed one.
I'm going to assume it's mine. All right. So with the textbook, this is chapter 10. We skipped over this long ago. Does it actually say it's a teacher edition?
No.
Okay. I'll need to make sure that one's actually mine.
All right. I have the other one at home, so I'll bring that one.
I'm going to hold that one as collateral. Just okay, you guys couldn't see that. It was a comedy of errors right there. All right. So anyways, chapter 10, we skipped over it. It was all about taking data that is not linear and making it linear. And just as a starting point, and I don't want you to overly stress on this because I'm going to show you what's most likely to be the case as far as questions related to this idea, because this is where it gets the most mathy as far as trying to remember all kinds of obscure things or that might appear obscure to you in the past. So if I gave you, I'm going to see what you guys can remember. If I gave you a graph that looks like this, what kind of function is that? Exponential. Good job. Now we come to the next part. What is the opposite of an exponential function? The inverse, I should say. No. What is it?
Exponential decay.
No. No. I'll give you a hint. The opposite of an exponential function looks like this. All right.
I remember this from biology. I think the people offline should be
Everyone in class is trying to outsource the answer to the people online. Does anyone know what we call that?
Isn't that a log?
Oh my gosh, see, you outsourced and she knew the answer. That's logarithmic. Okay, now you know it's the inverse because I didn't draw this very well, but if I drew y equals x right here, pretend that I drew that a little better. If I drew y equals x, you can see that this is basically a reflection. So if you switch your y and your x, you create your inverse operation. Logarithms become exponentials. Exponentials become logarithms when you do the inverse. Okay, so this one, I maybe started off with a more challenging one. So this is a, let's go with this. What would you call that? A parabola. And the type of a function would be a
y equals x squared.
yes. You're all right. You're all correct. I just want to see if you guys can come up with the other name for this. If I give you the first letter, you might. Starts with a Q.
Quadratic.
There it is, a quadratic. Okay.
What if you just have like an answer streak over your head? And then you got one wrong.
All right. So the inverse, let me go ahead and draw it like this. Oh, that looks so good. Look at that. It's the best parabola I've ever drawn in my life. Okay, you guys got to be witness to that. What is the inverse of a quadratic function? No.
I could draw it.
No, that's a good guess. Switch your y and your x, what do you end up with? Wait, y equals square root of x, is that what you said? Is that what you said? That's correct. Good. Okay, so if you switch this, so if you just switch those to inverse your function, then you can figure out that y equals square root of x. So the inverse of this is a square root function. So let's see if I can draw this one just as well. Oh my gosh, I should get a raise. Look at how good that is. So now normally when you're looking at a square root function, you're not looking at the negative part right here, but technically it's there. And so those are inverses of each other. All right. Now, we also have our functions that look like this. And honestly, I forgot the name of these types of functions. One of them I do know, but one of them I don't remember. What would be the, oops, I didn't want to clear. That's a bad thing I did. What might be the function, the actual expression on the right side for this function? I'm not sure if I'm making sense. 1 over x, there it is. So what do we call these things? Just rational functions? I don't know. So we can call this a rational function. Let's just go with that. So then if you switch, then what do we have when we switch this? Well, that's its own inverse, isn't it? Yeah. Well, whatever the case. So we have different ways. So there are functions here, and I wanted to point something out because this is kind of an odd one. There's another one right here that you won't deal with this function, at least mathematically. It looks the same as, if we're calling that a rational function, it looks the same, but this is what's called a power function, a power law. It's actually really, really interesting, and it is interesting to know about these for all kinds of reasons, but for our purposes, we have a power law. And I always get the two confused. One of them, ax to the b, ab to the x. I think this is your exponential, no. Yes, this is your exponential function. So this is your power function. Okay, now does all this matter? We're getting very mathy, right? We're talking about all kinds of graphs and functions that you haven't thought about in a long time. So here's the important thing, maybe as a takeaway. If you had there was something thrown out a minute ago, natural log. So your log and natural log are both equivalent in a sense mathematically. So it's just going to change the curve, but still you have your logarithms. And so if this is your e to the x function, this will be natural log of x. All right, so these two are inverses of each other. Now this doesn't maybe intuitively make sense, but if this was log base 10 of x, then the inverse of that is going to be 10 raised to the x. That one maybe makes a little bit more sense intuitively. All right, so if we're looking, and this is one that's probably going to make the most sense intuitively. If this is y equals x squared, then the inverse is y equals square root of x. And we can see that we can take this and this, which is the same as x to the 1/2 power. If I multiply those together, x squared times x to the 1/2, then I'm going to get just x. So when we transform nonlinear data, the idea behind this is we want to kind of figure out what shape does this data take. Is this a quadratic form? Is it an exponential form? Is it a logarithmic form? Like what shape is the data if it's not linear? And to make it linear, I want to do the inverse to it. So if I have data, now let's kind of make a scatter plot. So I've got data that looks like this, and I can determine that is not linear. And maybe my first thought is, I think that this line that's at kind of a best fit right here, this line is going to be quadratic. So if I want to make this non-quadratic, or this non-linear data quadratic, then I can take the square root of it. If I take the square root of x, then that's going to make it linear. So I hope this is making sense. If you have data fit one pattern, do the inverse to it, and you'll get linear data. Does that concept make sense at least? Okay. And I know you're probably, some of you might be getting a little freaked out, like, oh my gosh, we're going to have to do so much complex stuff with this. Luckily, we don't really have to. This is actually from your textbook. So the simple rule to remember, this is what I was just saying. Identify the type of equation shown and transform the data by the inverse of that function so that you can model the relationship with a linear function. And this is something you might find helpful here. So if you started off with an exponential scatter plot, then you can take the log of your y value, and then that's going to make your data linear. And a lot of times, if you're actually doing this in practice, sometimes you don't know exactly. So you could re-express this a number of different times. Take the data and say, is it exponential? No, that doesn't fit very well. Well, is it quadratic? Well, you can try that one, see if it works. So now let's kind of look at what is essentially going to be the type of question you have. Yeah, so there's, and then you can see right here with the power functions, it's, you have to take the log of both x and y. And this is also, I believe, kind of like your, if you do this in general, this is always like a fit everything sort of solution. I'm not talking very well. This is a good thing to try if you're not sure what kind of shape the graph is. So there we go. Now to put you at ease a little bit, you probably won't need to worry about re-expressing data directly. You're just going to need to figure out the predicted value of a regression equation that has been re-expressed. So, well, if you go back and look at that, you're just going to have to do a little bit of math on your calculator. And you're just going to need to remember it well enough to answer questions like this. So for every single model listed below, because these are all re-expressed equations based on data that was nonlinear to begin with. So they were re-expressed using log, and natural log, and other stuff. Here it was squared or 1 over square root. So with this, you just want to be able to plug this in. X equals 2. So I've got y hat equals 1.2 plus 0.8 times the log of 2. And of course, your calculator can do all this math for you. But it can get a little bit more challenging. So with this, it's pretty straightforward. I'm just going to do in my calculator literally 1.2 plus 0.8 times the log of 2. And your calculator automatically has a log base 10 on the left side. You're probably familiar with that. All right. And you guys can shout out or write on the screen whatever you get as your answer when you do this. $1.44. Everyone agree? Okay, I'm getting yes from Lily, so that must be correct. So I just want to, there's some people in class who are getting their calculators out now, so make sure everyone has time. This one is fairly straightforward. The next one will be a little less so. Now we've got the log of y hat equals 1.2 plus 0.8 times 2. The right side is very straightforward. So what does that come to when you evaluate the right side? 2.8. So talking about inverse, what do I want to do, or what should I do here if I want to figure out what y hat equals? Not the log of y hat, but actual y hat.
It's like the change of base formula where you move like, because like technically it's log base 10 to the y hat.
Oh, I know what you're saying. No, we don't need to worry about changing base.
Okay.
All right, and it's okay if you guys have forgotten or if you. So in this case, the opposite, the inverse of log is to do this. 10 raised to, I don't need that key right there. 10 raised to the log of y hat power, and I need to do the same thing to the other side. So if I do 10 raised to the base 10 log of y hat, these two operations actually cancel each other out. So I end up with y hat equals 10 to the 2.8 power. And that we can plug in. And there's actually a function on your calculator. If you go to your log button and you do second, and that you can just raise to the 2.8 power. So go ahead, shout out or write down what you find when you get that.
I got 630.96.
All right. So we are having to review some math concepts that you might not have thought about in a day or two. But if you can recall this stuff, you can see the math questions really aren't so bad. Okay. If we look at the next one, and I think the D and E are pretty straightforward because it's just dealing with squared stuff. We can go through that if you want to, but let's just do part C. In fact, I'm not going to put the answer down. I'm just going to do this much right here. Natural log of y hat is equal to 1.2 plus 0.8 times the natural log of 2. Now, if you get to a point where you get stuck, don't worry about it. We will run through this problem, but I want to see if you guys can come up with the answer for what y hat equals. Okay, so with this right here, there we go. I can see 5.78, 5.78 coming in. So the right side is pretty straightforward. You can find your natural log button just 2 above your on button. So on the right side, I'm guessing everyone was able to come up with this. Natural log of y hat equals 1.7545 ... So the question is, what's the inverse of natural log? And even if you never had a class where you dealt with this, but I'm feeling everyone at least has worked with natural log to some degree. So if you don't remember the inverse of it, the good thing about it is on your calculator, the inverse is always the second function. So if natural log is your function, then e to the x power is your inverse of that. So what we're doing is we're not raising this to the power of 10 or 10 to the power of this. Instead, it's going to be e, which is the inverse function. So e to the 1.7545 power. And that's how we will get our y hat, which is going to be 5.78. If you got 5.75, you might have rounded this 1.7545 a little shorter, but you're in the same ballpark. Okay, are there questions on that one? So I don't know if you want to take a note on this, anyone who maybe isn't as familiar with logs. So if you have a log of x, that's technically log base 10. So the inverse of that, which I'll draw like that, that technically means inversely related, is going to be 10 raised to the x power. Natural log of x is another way of saying log base e to the x. So that means that the inverse of that is going to be e to the x power. Okay. Again, maybe stuff you didn't expect to have to deal with when you signed up for a stats class, but you only have to deal with it a little bit. So I'm assuming that you guys will be okay with D and E. Maybe what we can do is we can just confirm the answers to both of these. So maybe before we leave this page, let's just write down the answer to D and E. And then if there are questions because you didn't get the same thing, then we can talk about that more. So y hat and y hat. This will be for D and this will be for E. Okay, I like both of those answers, 1.67 for D, 0.128 for E. I am guessing these two are simpler for you guys to go through and solve compared to B and C, because it's a little fresher as far as how we work with squares and square roots. If you didn't get those answers, then feel free. Certainly we can stick around and we can go through kind of the full algebra for this. But assuming that you're all good with that, I'm going to move us forward. Okay, we are going to be looking at linear regression inference. And what I encourage you to do is look over chapters 7 to 9, which was unit 3. Unit 3. Yeah, that's right. So if you want to just go over and remind yourself about some of the things related to linear regression, like your regression line, the equation for the slope, and remember that is on your formula sheet. So this stuff right here, especially these bottom two formulas and the bottom 4, that's going to include your regression equation and things like that. So if you want to just remind yourself of some of those rules, that'll be good to know. And as far as that goes, let me see. We're not going to be looking at the project yet. I'm going to wait to describe the project until we are done. That'll be next week. So I'm going to skip over all that. It was a relatively short class today. So chapters 7 through 9, read through that. Chapter 27 is where we're actually doing the linear regression inference. And tonight for homework, you have very little to do. You have one problem. So pretty straightforward. If you have any questions on any of this or any previous stuff, let me know. Otherwise, you can have yourself a wonderful day, and I will see you guys tomorrow.